The engineering behind modern bridges. Modern bridge engineering considers many factors, including materials, load-bearing capacity, and environmental impact. The goal is to create safe, functional, and visually appealing structures. Steel, a strong material used in bridges. Concrete, a classic material used in bridges. A bridge is a structure built to span a physical obstacle, such as a body of water, valley, road, or railway, without blocking the path underneath. It is constructed for the purpose of providing passage over the obstacle. There are many different designs of bridges, each serving a particular purpose and applicable to different situations. Designs of bridges vary depending on factors such as the function of the bridge, the nature of the terrain where the bridge is constructed and anchored, the material used to make it, and the funds available to build it. The earliest bridges were likely made with fallen trees and stepping stones. The Neolithic people built boardwalk bridges across marshland. The Archidiko Bridge, dating from the 13th century BC, in the Peloponnese is one of the oldest arch bridges in existence and use. Bridges can be categorized in several different ways. Common categories include the type of structural elements used, by what they carry, whether they are fixed or movable, and by the materials used. A world of bridges. Bridges may be classified by how the actions of tension, compression, bending, torsion and shear are distributed through their structure. Most bridges will employ all of these to some degree, but only a few will predominate. The separation of forces and moments may be quite clear. In a suspension or cable-stayed bridge, the elements in tension are distinct in shape and placement. In other cases, the forces may be distributed among a large number of members, as in a truss. The materials used to build the structure are also used to categorize bridges. Until the end of the 18th century, bridges were made out of timber, stone, and masonry. Modern bridges are currently built in concrete, steel, fiber-reinforced polymers, FRP, stainless steel, or combinations of those materials. Living bridges have been constructed of live plants such as Ficus elastica tree roots in India and wisteria vines in Japan. Material and construction: a symphony of strength. Unlike buildings whose design is led by architects, bridges are usually designed by engineers. This follows from the importance of the engineering requirements, namely spanning the obstacle and having the durability to survive, with minimum maintenance. In an aggressive outdoor environment, bridges are first analyzed. The bending moment and shear force distributions are calculated due to the applied loads. For this, the finite element method is the most popular. The analysis can be 1-, 2-, or 3-dimensional. For the majority of bridges, a 2-dimensional plate model, often with stiffening beams, is sufficient, or an upstand finite element model. On completion of the analysis, the bridge is designed to resist the applied bending moments and shear forces. Section sizes are selected with sufficient capacity to resist the stresses. In most countries, bridges, like other structures, are designed according to load and resistance factor design (LRFD) principles. In simple terms, this means that the load is factored up by a factor greater than unity, while the resistance or capacity of the structure is factored down by a factor less than unity. The effect of the factored load, stress, bending moment, should be less than the factored resistance to that effect. Both of these factors allow for uncertainty and are greater when the uncertainty is greater. The future of bridge: innovative solution. Types of bridges. For small footbridges, the cantilevers may be simple beams. However, large cantilever bridges designed to handle road or rail traffic. Suspension: the cables are usually made of steel cables galvanized with zinc along with most of the bridge, but some bridges are still made with steel-reinforced concrete. Arch: bridge stone, brick, and other such materials that are strong in compression and somewhat so in shear. Beam bridges can use pre-stressed concrete, an inexpensive building material, which is then embedded with rebar. Truss: the triangular pieces of truss bridges are manufactured from straight and steel bars. 3D printing can significantly assist in building bridges by enabling the creation of complex, optimized designs with minimal material waste, allowing for faster construction times, and facilitating the integration of intricate features while providing greater design freedom compared to traditional methods. Essentially, it allows for precise, Layer-by-layer construction of bridge components with customized shapes and functionalities, potentially reducing costs and environmental impact. Renewable energy can significantly contribute to an innovation bridge by driving the development of new technologies, creating a market for cutting-edge energy solutions, and fostering collaboration between industries and research institutions, ultimately leading to a more sustainable and efficient energy system across various sectors. Overall, by driving the need for new technologies, creating new markets, and fostering collaboration, renewable energy acts as a crucial catalyst for innovation, promoting a sustainable energy future across various industries and sectors. Solar energy can innovate bridges by integrating solar panels directly onto the bridge structure, generating electricity to power lighting, monitoring systems, and even potentially contribute to the bridge's overall energy needs, while also providing a shading effect that can help mitigate temperature-related stress on the bridge materials, thus extending its lifespan and improving its functionality.